Hey guys, welcome to another action-packed episode of Let's Do Some Maths. It's gonna same paper as last video, Jan13, still FP2 AQA. I'm gonna be having a look at question 8 this episode. Question 8 is about complex numbers. No one likes complex numbers, the clue's in the name really. Yeah, so open your question papers up to question 8 and let's have a go at it. So 8a. First thing we have to do is express the complex number minus 4 plus 4 root 3i in its exponential form. So there's a few different ways you can write complex numbers with its real and imaginary parts like this. You can write it as cos theta plus I sine theta multiplied by r, the modulus, or you can write it in its exponential form, which looks like z equals r e to the I theta, where r is the length of the complex number, the modulus, and theta is the argument. So let's draw this on an R-GAN diagram and it might help us a little bit. You don't need to do this, but I like to. I definitely think later in the question, though, you will need to use R-GAN diagrams. So why not pop one out right away? So minus 4 root 3i would be about there. So let's mark the lengths on, because that's going to help us work out the angle and the argument. So this would be 4 root 3, and this length would be 4. Now remember, and this is really the only place where people can go wrong in this question, remember that the modulus is measured counterclockwise from the line real is equal to 0. So the modulus is this angle here. I'll call that theta. Well, yeah, we should call that theta. Some people might be tempted to find this angle here, which I'll call gamma for the time being, and call that the modulus. But it isn't the modulus, so just be a little bit careful of that. Okay, now how are we going to work this out? To work out the argument, r, it's quite easy, just a little bit of Pythag. So we square both the sides, 4 squared plus 4 root 3 squared, and square root the whole thing. So that gives us 16 plus 4 squared is 16, root 3 squared is 3, so 16 times 3 is 48. So that gives us root 64, which makes you feel nice and confident you've done the numbers right, because that works out to a whole number. That's 8. How do we work out gamma? Well, we've got the adjacent, we've got the opposite. That means we use tan. So gamma is the inverse tan of the opposite, which is 4 root 3, divided by the adjacent, which is 4. The 4's cancel out to give you the inverse tan of root 3. That is a common angle, so you should remember that that is pi on 3. So this angle here is pi on 3, but to find theta then, we'd have to take pi on 3 away from pi, because 180 degrees is pi. So theta is equal to 2 pi on 3, and that tells us that the complex number z is equal to 8 multiplied by e to the 2 pi I on 3 for 3 marks. Nice and simple really, wasn't it? Pythagoras and a bit of trigonometry. GCSE, really? It is once you know what complex numbers are. Right, part B. So we're going to solve the equation now. Z cubed, is that right? Or is that later? Yeah, that's right. So we want to solve this equation. Z cubed is equal to minus 4 plus 4 root 3i. But we found out in the last question that that is equal to 8 multiplied by e to the 2 pi I on 3. So what we want to solve is z cubed equals 8e to the 2 pi I on 3. Now straight away, well, we've got z cubed, so we could raise both sides to the power third to get rid of that cubed. So you could cube root the 8 and you could divide this power by 3. Great. that would give you a solution, but that doesn't give you all of the solutions. Remember, for z cubed to the power 3, we're looking for 3 solutions. So what we need to do is find 2 more complex numbers that are equal to this number here that are going to generate our 3 solutions. But we also must remember to have a look at the range that we're allowed to give our solutions in, because we're only allowed to give theta between minus pi and pi. So that's going to come into play later. Now, how do we generate then 2 more, to give us 3 in total, how do we generate 2 more complex numbers that are identical to this? Well, think about your Argand diagram. So 8e to the 2 pi I on 3, we said that was over there, didn't we? 8e to the 2 pi I on 3. So you've gone around 2 pi I on 3 to get there. If you want a number that's identical, what you can do is just go around the whole Argand diagram again until you get back to here. So the first time you go around 2 pi on 3, but then the second time you go around once, all the way around the Argand diagram, and then around 2 pi on 3 to end you back up onto this complex number here. So all we need to do then is add 2 pi onto the argument of this, and we'll do it again to go another once more around. So our 3 numbers then are z cubed equals 8e to the 2 pi on 3, the original one. Then we add another 2 pi onto that, so 2 pi is 6 pi on 3. So if we add 6 pi on 3 onto that, we get 8 pi I on 3. And if we add another 6 pi onto that, we'll get 14 pi I on 3. Cool. And now we can raise both sides to the power third to get rid of this cubed here. So z equals the cubed root of 8, which is 2. And then we divide the power by 3. So 2 pi on 9. Well, that's under pi, so that's in our interval. We're all good. The next one then, 2e to the 8 pi on 9. That's just less than pi, so that one's good, but it probably means the next one is not going to be good. Next one, 2e to the 14 pi I on 9. Now that's bigger than pi, so that's not a valid solution. So again, we need a complex number that's equal to that one, but with an argument between minus pi and pi. So to get that, we have a look at where this is on our Argand diagram. On our Argand diagram, be about here. 2e to the 14 pi I on 9. So to get to that number, I've gone clockwise around 14 pi on 9. But what I can also do to get to that number is go counterclockwise. But if I do that, I must remember that the argument becomes negative. So when you start going counterclockwise, the argument becomes negative. Now, all the way around is 2 pi, which would be 18 pi on 9. So the difference between 14 pi on 9 and 18 pi on 9 means that this angle here must be 4 pi on 9. So this is outside of the range, but the one inside our range, the complex number equal to this, that's inside our range, would be 2e to the power minus 4 pi I on 9. Cool. So in the next part of the question, what we're going to do is sketch those 3 solutions on an Argand diagram and find the area of the triangle that they create when you join their points up. And this requires a little bit of thought. When you're plotting the points, sort of think how you're plotting them, Because all solutions to this, all solutions like this to complex equations, when you plot the solutions, they all follow a pattern. They go around the Argand diagram in the same step each time. So you might go around in 45 degrees. You might have solutions, or pi on 4. So you might have solutions, like I say, that go every 45 degrees. And you just add 45 degrees on each time. So your solutions always work in a pattern like that, where you have your first solution and then the other solutions you're just adding the same angle on each time. And that's going to help us here. So let's plot our solutions then. We've got e to the 2 pi I on 9. That would be about here. And then we go 6 pi I on 9 around to get us to e 2e to the 8 pi I on 9. And then we add on another 6 pi I on 9 to get us around to e to the to the minus 4 pi I on 9. And we want the area of that triangle there. And I haven't drawn it amazingly, but hopefully you'll be able to see what I'm about to show you. So, we've gone the same amount of degrees all around our Argand diagram. Now what that means is that these, essentially, because they all have the same argument, they all have the argument of 2, so they're all the same length. So what that means is that these 3 points lie on a circle, because they all have the same distance from the centre of our Argand diagram here. And because so I can also draw on the radius here. So the radius we know is always 2. Now, so we've got radius of 2, radius of 2, radius of 2. And like I was saying, because of the pattern with complex solutions, we've gone the same amount of degrees, or radians, between each of these lines. So the first solution was at 2 pi I on 9. Then to get to the next solution, we added on 6 pi I. We added on 6 pi on 9. Then to get round to the next solution, we added another 6 pi on 9. And then to get round to the last solution, we added another 6 pi on 9. What I'd like you to do now, maybe pause this video for a couple of minutes, draw this diagram out, make sure you've got it drawn out, pause this video, and then see if you can see what's important or what's interesting here. What's going to help you with this question. Okay, pause it now. I'm going to take a little drink. Okay, so hopefully you've had a look at that diagram for yourself, and hopefully that you can see what we've done is we split this big triangle up into 3 equal triangles. They've all got 2 sides with length 2, and they've all got the angle in the middle being 6 pi on 9. So you've got 2 sides and you've got the angle in between. Again, a little bit of GCSE, but you don't really need that. That tells us that all these 3 triangles are equal. They're all similar triangles. Well, is that what they're called? Can't remember what name. Congruent. They're congruent triangles. So, to work out the area of the big triangle, we're going to do 3 lots of the area of those little triangles. And the area of the triangle is a half AB multiplied by sine of the angle between them, sine C. Half AB sine C. We usually write the sides out in small letters like that. So 3 times the area of the big triangle then is 3 multiplied by the area of a small triangle. So that's a half multiplied by 2 by 2 by sine of 6 pi on 9, which is sine of 2 pi on 3, which again is a common angle. So sine of 2 pi on 3 is, well, you can, this is a common angle. You can take it from here. I can't remember. How's it go? You've gone in 30 to get to a half, 2 pi 3. It's root 3 on 2, I think. Root 3 on 2. So 3 lots of root 3 might be the final answer there. Maybe. Yeah, 3 lots of root 3. Cool. There you go. Okay, last question. They want you to consider the roots of that equation and show that something involving causes is true. Okay. So we've got the equation. Z cubed is equal to minus 4 plus 4 root 3i. And we know that has solutions 2e to the 2 pi I on 9, 2e to the 8 pi I on 9, and 2e to the to the minus 4 pi I on 9. And we have to consider the roots of this equation and get to where they want. They want something involving causes. You add 3 causes together and they equal 0. So you've got to think, we've got a cubic equation here. Think, and this is an FP2 topic, how do the roots of cubic equations work? How can we get an equation where we're adding things up, something to do with the roots probably, we're adding things up and we get that equal to 0? How can we get something that looks like that? Well, you should know that if we have the equation ax cubed plus bx squared plus cx plus d is equal to 0, if that has roots alpha, beta, gamma, then you should know that alpha multiplied by beta multiplied by gamma, that equals something. Alpha beta plus alpha gamma plus beta gamma, that equals something else. We don't really want to use any of those here because we've got something plus something plus something. So what we probably want to do is find out what the roots added together make. So alpha plus beta plus gamma usually makes b over a or minus b over a. I should probably get it right. Yeah, minus b over a. So alpha plus beta plus gamma equals minus b over a, where b is the coefficient of x squared. Well, here we've got no coefficient of x squared. We haven't even got a coefficient of z squared, which is what we'd be looking for. So the roots added together here must equal 0 because, well, b is 0 in our equation. So if we add these 3 roots together, we're going to get 0. And now I know I've done something very similar to this in the past, so I might leave this here, but let's see how it goes. So 2e to the 2 pi I on 9 plus 2e to the 8 pi I on 9 plus 2e to the minus 4 pi I on 9 equals 0. Great. So it's looking a little bit closer to what the answer has, but still not quite there. How can we get this then in terms of causes? Well, we can't get it in terms of causes straight away, but what we can do is write each number out in its sine cos form. So r lots of sine theta plus cos theta plus I sine theta. So I think I'll do that for each one, and then I'll just talk about what's going to happen. So the first one then, 2 cos 2 pi on 9 plus I sine 2 pi on 9 plus 2 lots of cos 8 pi on 9 plus I sine 8 pi on 9 plus 2 cos minus 4 pi on 9 plus I sine minus 4 pi on 9. And that's equal to 0. Now, when you have a equation with reals and complexes in, and that equals something else, you can say the real part is equal to the real part on this side, and the imaginary part is equal to the imaginary part. So that means 2 lots of I sine plus 2 lots of I sine plus 2 lots of I sine, that equals 0. You can just get rid of that, because we're not interested in that, we're only interested in causes. So 2 cos 2 pi on 9 plus 2 cos 8 pi on 9 plus 2 cos minus 4 pi on 9, that equals 0. Divide everything by 2 and change the minus 4 pi on 9 to plus 4 pi on 9, because cos is an even function. It's symmetric about the line x equals 0. Cool, okay. My throat has hurt this episode, so that's why I'm going to stop there. Yeah. Cool. Okay. No one likes complex numbers today. No. Rubbish. I hope that's helped. I think so I've done a question like this before. You should know that. The interesting part here, other than remembering to keep your argument theta between minus pi and pi, or 0 and 2 pi, whatever range they happen to be asking for, you have to make sure you get that right. That's why I've seen a lot of people lose marks. But the only other, I think, interesting thing here was a triangle. And realizing that because you always go the same amount of degrees around to get to each solution, then you can split them up into 3 triangles that all have the same angle in the middle, and they all have the same argument because they're 3 points on a circle. And you always get that whenever you're dealing with complex numbers like that. So I can imagine a really awesome question, and this is the kind of thing they're doing now, because they're getting harder, they're getting trickier. We've seen that last year. Why not ask you to give the area of a pentagon or a hexagon or an octagon? You know, if you had eight solutions like this, well, you could find out the area of that octagon by realizing that it's that triangle here multiplied by 8. Could be a question. Who knows? If it is, I'm going to want some money, or at least something like that. Okay. See you guys. Good luck.